Welcome back for part 2 of the Unit 1 review. Hopefully you guys have already watched through the first part, understood that completely, and were able to answer the first free response practice question. This next video is going to deal with the biogeochemical cycles only. This is a very, very important part of our AP exam, usually a very, very big part of our AP exam. I'm not quite sure how this is going to work with the new format of it, but my guess would be that biogeochemical cycles are going to show up somewhere within it, whether it's part of an experiment or part of a describe type of thing where they want you to link that biogeochemical cycle in. So what we're going to focus on are the different cycles and how they're going to happen, what's going to occur within them. So with the first cycle, the carbon cycle, there's going to be 4 different processes primarily that are involved in it. We have respiration, photosynthesis, combustion, and decomposition. With respiration, it's the opposite of the photosynthetic reaction. So you absolutely need to know that photosynthesis, let me make this a little bit smaller here, photosynthesis is going to be carbon dioxide from the atmosphere reacting with water that's out there. And then it's going to form sugar, and it's going to form oxygen gas. These products are both extremely, extremely important. The sugar is what's going to provide us our energy. And again, it's energy in the form of ATP. Those sugars are going to be converted into ATP. That gives our cells energy, allows our bodies to function, or it allows living organisms to function, whether it's a producer or a consumer. The oxygen, again, is important because that's what allows us to breathe. I don't think you're going to need to know the balanced reaction, but just know it's 6s in front of everything except for the except for the sugar. The sugar just remains a 1. With respiration, and it's important to note also that you have to have sunlight in order for that reaction to have enough energy to convert those carbon dioxide molecules into sugar. For respiration, it's the opposite reaction. So you're going to have the sugars that were produced. Plants and animals are going to use those for energy, so they're going to consume oxygen to help break those apart, and it's going to give off carbon dioxide as they exhale, and it's going to give off water vapor as well. And then we have energy as a product as well. And again, this is going to be energy in the form of ATP. So those first 2 reactions are the primary fueler of that carbon cycle. Even if humans weren't on the planet, we would have the photosynthesis and respiration happening with our plants and animals. So even without looking at anthropogenic influences of the carbon cycle, this is going to be that natural carbon cycle. Then in addition to that, we have combustion, which takes hydrocarbons, organic material. It's going to use oxygen, and it's going to break those down into carbon dioxide and water. Now, that's assuming we have unlimited amounts of oxygen and we have more than enough oxygen to supply the necessary oxygen to produce, to completely react, all those hydrocarbons. If we lack enough oxygen, then it's going to produce carbon monoxide instead. So this combustion reaction, again, that could be natural forest fires. It could be human set fires in our fireplaces, or burning fossil fuel energy to produce electricity or to produce heat, whatever it is. So the combustion can be both a natural and an anthropogenic part of the carbon cycle. The last one is decomposition. Decomposition is nothing more than respiration, but it's important to note we have 2 different types. We have anaerobic and we have aerobic. Take a second, think about what anaerobic and aerobic mean. Hopefully you guys came up that anaerobic means there's no oxygen present. Aerobic means we do have oxygen. So if we're looking at aerobic respiration, aerobic decomposition, it's the same basic principle as what cellular respiration is, because it's being performed by bacteria. Those bacteria are taking in the sugars, they're breaking it down with oxygen present to produce carbon dioxide and water. But if it's anaerobic, that's where it's a little bit different. The bacteria are going to take the sugars in, but they're not having oxygen available to break them down. So instead of it producing carbon dioxide and water, now we're going to get the methane and water vapor. It's still going to produce energy, but it's going to also produce the methane as opposed to carbon dioxide. With aerobic respiration, it's going to produce carbon dioxide in water. So these are the main steps in that carbon cycle. But it's important to note also, we have fossil carbon and modern carbon. Fossil carbon is the carbon that should be stored or sequestered for long periods of time. Sequestered, sorry, I'm trying to spell and think at the same time. Sequestered for millions of years. So think about what types of fossil carbon we would have in the world. Hopefully you came up with our fossil fuels, and that's why they call them fossil fuels. It's fossilized forms of carbon. So our coal, our oil, our natural gas, you could even get into diamonds with that because those have been compressed forms of carbon. But mainly they're talking about the coal, oil, and natural gas. Those deposits would have been underground forever if humans weren't in the system. So we took carbon from long ago from the atmosphere, trapped it within those tissues of the plants through photosynthesis. As those plants then died, they fell to the bottom in aquatic zones. They started to have sediment stacked up on top of them, filling them in over millions of years with tons and tons of sediment. That heat and pressure that they were exposed to converted it from the traditional organic material and allowed it to be partially decomposed. And as it was squished under that heat and pressure, that's when it formed the coal, the oil, and the natural gas. Depending on what the organic material was and how long it was exposed to those temperatures and pressures determines what type of fossil fuel it was. So when we look at the modern carbon, this is going to be the stuff that's cycling naturally or even anthropogenically. That sequestered carbon was really important for us because that took carbon that was from the atmosphere millions of years ago, trapped it underground, and didn't allow that to go up into the sky. So it helped to maintain kind of an equilibrium amount of carbon dioxide in our atmosphere. Now, when we started to mine for that coal, oil, and natural gas and started to burn those, now we're putting excessive amounts of carbon dioxide up into the sky. So if we're just looking at these 4 steps here in the non-anthropogenic carbon cycle, it would exist as equilibrium. For every molecule of carbon dioxide that's released into the atmosphere, another one would be taken and being absorbed. But as we're taking that fossilized carbon from underground and releasing it up into the sky by burning it, now we're adding carbon dioxide that can't be absorbed by the plant material. We don't have enough photosynthesis to counteract all the carbon dioxide we're releasing. So that's where we get into the modern carbon cycle. That's where we're doing these respiration, photosynthesis, and decomposition still, but we're increasing our rates of combustion of that fossilized carbon. When we're doing that, we're increasing carbon dioxide levels in the atmosphere. Now, why is that a problem? Think about it for a second and try to come up with 2 reasons that's a problem. All right, so the first reason that you guys probably came up with is that carbon dioxide is a greenhouse gas. That's 100% correct. It traps and absorbs heat up in the atmosphere. The more carbon dioxide we have, the more heat holding capacity the atmosphere has. As that sunlight, if this is our atmosphere and this is the surface of the earth, as the sunlight comes down, hits the planet, and is reflected back upwards as infrared heat energy, those carbon dioxide molecules are absorbing that heat energy and trapping it in our atmosphere. If those carbon dioxides weren't there, that heat energy would just escape and dissipate into outer space. The more carbon dioxide we're putting in, the more of that heat that gets trapped and stuck in our atmosphere. So our global temperatures are going to rise. As the global temperatures rise, that's going to create one of those feedback loops where we have more carbon dioxide means more heat is being absorbed. More heat being absorbed traps more heat energy in, starts to raise the global temperatures. As the global temperatures start to rise, now we have more permafrost melting. More permafrost melting means more release of those greenhouse gases that would have been trapped and frozen underground for extended periods of time. But since we're raising the temperature of the planet, now that permafrost melts and we have far more carbon dioxide and methane being released. The more of that in the atmosphere, again, the more heat holding capacity we have. More heat holding capacity just keeps on reinforcing that loop and creates that positive feedback loop. So again, CO2, greenhouse gas. Second way that it's affecting us is if we look at our oceans. if we have excessive amounts of CO2 in the sky, that CO2 is going to readily dissolve into the water. It's going to be trapped in the water either through wave action or just anytime it's at the surface of the water, some of it's going to get trapped and dissolved in. As that carbon dioxide dissolves into the water, chemical reactions are going to happen. So if we're looking at it in terms of the oceans, oceans represent, again, over 70% of our land mass. Well, I can't say land mass, 70% of the surface of our planet. So that carbon dioxide is going to get trapped in the oceans. As it reacts with the water that's in the ocean, it's going to form carbonic acid, which is H2CO3. Excuse me, that carbonic acid then is going to lower the pH of the water. So the pH is going to fall, and that's going to adversely affect the plants and fish and animals that live in the ocean. Because again, we have that optimal range of tolerance. If they can survive at a pH range from say 6 to 7.5, now if we lower that pH and now the ocean water goes to a pH of 5, those animals aren't going to be able to survive, grow, and reproduce. They may be able to survive and grow depending on what the pH is, but they're no longer going to reproduce. Anytime they're not reproducing, they're not replacing their parents and the offspring, and we see our population, again, that would be at the carrying capacity, but now that pH is falling, it's going to cause that population to crash because they're no longer reproducing and replacing the parents that are dying. So that's the carbon cycle. If you guys have any questions on that, please email me. I'll answer any questions you guys have. The other big cycle that we have is the nitrogen cycle. And there's an acronym to remember this. And I would suggest, again, having a one-page review sheet for every unit. That way, when you're taking the AP exam, you can just say, all right, hey, this is a nitrogen cycle question, which was in Unit 1. I have my one-page sheet that's going to allow me to review for that. And we'll be walking you through how to create those one-pagers as we go. I think I have a pretty good setup going right now that you guys can use as a backbone, and you'll be able to kind of adapt them to put extra information on that you want. But the acronym is FIXNAID and PAN. FIXNAID are the processes and PAN are the products. So if we look at FIXNAID, the fix part is for fixation. We have biotic and abiotic. So when you think about abiotic, what are you thinking of? Good, you should have said non-living. When we have biotic, that's going to be living material. So this one is done by bacteria. This one is going to be done by lightning. The end product is going to be ammonia. So what we have here is the N2 gas. Again, nitrogen gas is inert. It doesn't react. It's triple bonded. Those triple bonds are extremely, extremely strong. So there's only two things that are strong enough to break that. We have the bacteria in the soil, and we have lightning in the atmosphere. So if it's atmospheric nitrogen, it's going to be broken apart by lightning. If it's nitrogen gas trapped in the ground, it's going to be done by bacteria. But either way, the N2 is going to give us ammonia, which it's first going to be NH3, but then the NH3 reacts with the water to form NH4+. This is the usable form for plants. Now we took something that's inert, the N2 that's inert, and we made it into a usable form. Plants don't like ammonium though. What they do like are the nitrates that we have being produced. And that's where nitrification comes in. Again, this is done by bacteria. And it's going to take the ammonium ions, and it's going to create first nitrite, which is NO2, and then it's going to further react those and form nitrates. That's all done by bacteria. Two different types of bacteria. One makes the nitrite, the other makes the nitrate. Then, as we have that nitrate being produced, that's another usable form by plants and animals. So we have assimilation happening. Assimilation is where it's just absorbed into the plant matter. It's going to be created in the proteins. Then the plants are able to have the nitrogen they need. The animals then eat the plants to gain the nitrogen that they need. So we have NO3 or NH4 changed into protein. Right? As those plants and animals are eating those proteins, and as they start to die, the plant matter dies, or the animals poop, or the animals die themselves, they're going to undergo ammonification. And the ammonification is going to be done by bacteria again. and it's going to take the protein and convert it back into ammonia. And again, it's NH3, but then it reacts with the water in the ground to change it into NH4. Now, that ammonia is where it either gets fed back into the fixation process, or sorry, back into the nitrification process, or it can be further broken down and release this nitrogen gas back up into the sky. So this one here can either go two directions. It can either go back and be used in nitrification, or it can go downward and be part of denitrification. And again, this is going to be done by bacteria, and it's going to be primarily in swampy conditions because the bacteria that are doing this denitrification love to have, excuse me, harsh conditions, low oxygen levels. If it's in one of those types of environments, then it's going to go back into that denitrification way. If it's not in those types of environments, then that ammonia gets put back into the soil to be used as a nutrient again for living material. So if it's in swampy areas, it's going to take the ammonia / ammonium, and it's going to release it as N2 gas. That N2 gas goes up into the sky, which then in turn gets refixed and the reaction starts back up again. This is the nitrogen cycle. It's one of the most important ones. What you guys need to do as you're going through all these different chemical cycles is understand how we're affecting the cycles. You know, with the carbon cycle, we were burning the fossil fuels. We were releasing more carbon dioxide into the sky than what we ever had in the past. Carbon dioxide that should have been stored for millions of years. We released that in a short period of time and overwhelmed the system. With the nitrogen cycle, we're adding synthetic fertilizers. Those synthetic fertilizers are going to be in the form of ammonia or nitrates. So what we're doing is we're overwhelming that nitrogen cycle. By overwhelming it, we're putting excessive amounts of nutrients into the soil. When we put those excessive amounts of nutrients into the soil, they tend to wash off the surface of the ground. They then go in the bodies of water, which stimulate algal growth. Remember that eutrophication process. If you don't remember what eutrophication is, make sure you Google it and review it. Because again, anytime we have excessive amounts of nutrients, that's going to create those eutrophic conditions. All right, that's the nitrogen cycle. The last two are not as important, but they still have a couple key features. With the phosphorus cycle, I don't remember them ever asking questions about the phosphorus cycle with the exception of three things. First one is that it has no atmospheric component, meaning it all takes place in the ground. It's also the slowest cycle. It's geologic because it relies on the rock cycle in order to occur. The phosphorus is trapped within rocks. The rocks have to physically and chemically weather to release those phosphates. It's the main limiting nutrient because of that. Since it's taking geologic time, it's going to take hundreds of thousands of years for that phosphorus to be released. The phosphorus we have available to us right now then is in limited supply. As it's used up, we don't have a whole lot of new phosphorus coming in. So what we're doing is to help speed up our plant growth in farms, we're starting to mine for phosphate-rich rock. When we mine for that phosphate-rich rock, we crush it up, extract the phosphates out, and use that as a chemical fertilizer. So we're putting more phosphorus into the system than we ever had in the past. And again, since it's the main limiting nutrient, once we free up that limiting nutrient and it's no longer limiting, now we have explosive plant growth. When we have that explosive plant growth, it's sometimes the plants that we want to grow, crops and things like that. But if it runs off into the water, the explosive plant growth we see is the growth of algae. As that algae grows, some of it dies and starts to be decomposed. If you think back to the carbon cycle, when it's decomposing, it's consuming the oxygen from the water. So as the algae grows, due to the excessive amounts of phosphorus in the waterway, now we start having the oxygen start to be robbed of from the water rather. The oxygen levels start to decrease in the water due to the fact that the bacteria are breaking down the dead organic material from the algae. All right, and our last one is the water cycle. Everybody should really know the water cycle, with the exception of maybe the transpiration process. Transpiration, again, if you remember back to when we talked about this, transpiration is the water that leaves the leaves of plants. So if this is our plant leaf here, there's those little openings, those stoma within the plants. So those leaves have those little openings. As the sunlight hits the plant, it heats up the water in the tissues. And that water then starts to exit the leaf. That's the transpiration process. It's the same as evaporation, but only now instead of it happening at the surface of water. So whenever you have a body of water and the water vaporizes and goes in the gas form, that's evaporation. When it's happening out of leaves, that's transpiration. Usually what they do is they combine these and call it evapotranspiration. Because it's the water that's going up into the atmosphere. That water that goes up in the atmosphere, it's the number one natural greenhouse gas. Water holds on to heat very, very well. But the reason we don't put that into the anthropogenic uh, greenhouse effect is because water doesn't have a long residence time in the atmosphere, meaning it doesn't stay in the atmosphere very long because as it evaporates or transpires, it has to absorb energy to do that. That energy, though, goes away fairly quickly. So it's going to recondense, relatively quickly in the sky. So we have the evapotranspiration putting it into the sky. It condenses in the clouds, the concentration of the water increases, and eventually we have precipitation, rain, snow, hail, whatever it is. That then creates the runoff when it hits and can't soak into the ground. If it's able to soak into the ground, that process is called percolation. That's what's going to help to distribute the water across the planet, and it's fueled by our sun. Now, that's where I'm going to stop at for this video. It's already 20 minutes. We'll talk about productivity, and then we'll end the Unit 1 review.